This information is brought to you by Charles Sturt University.
A lot of the stuff about combinatorics, the counting stuff we've been doing, was developed because of probability.
It's always 50-50 though. 50-50. Either it is going to happen or it's not.
Right. Yeah, that doesn't mean, that's not it's 50-50.
It's like, or you're either doing two things at any given time. You're either playing Connect 4 or you're not.
Okay, so it's not that early.
50-50 chance you're a potato, David. If you're a potato.
Alright, let's start and we'll let people walk in slowly. So we've been looking at different ways of counting things, and the reason for doing some of that, reminding ourselves, is sometimes when we do algorithms, you just need to know how many things there are, whether you want to just brute force it or not. And so sometimes when you've got a really large sample, you go, well, sometimes you want to take a random sample of it all. And so just a way to talk about taking random samples or just talking about making choices is using probability as a useful technique behind it. And so if you're making a computer game, some of you guys might be interested in later down the track, you'd like to make the game not predictable. Because people learn it and then they can defeat you pretty quickly. So if you can randomise things, you can make the game last longer, etc. So we're looking at language of probability, and even if you're not going to be in here with games, so you don't care about games at all, then you might be doing a simulator, or you may be developing a site you want to just work out if your website's going to handle different models for a load. So is your server going to handle it all the time? Now, when people rock up to your site is a random event. And there's different probabilities of how many people you get at a certain time. And you want to know, well, how much of the time is your server going to be able to handle it? Now, I'm sure Pokemon Go tried to do that and they just estimated wrongly, I suspect.
Actually, no. Europe fucked us over. Yeah, that's about it.
There you go.
Europe screwed us.
The problem is they only have 100 employees, and they tried for a world road release, and it was it's not something that you want to do.
So, where probability started was not Pokemon Go, but it was back in 1654.
How dare you?
It was back when they were trying to understand gambling better. Now, so I discourage gambling, and when I show you the probability of winning lotto, which really discourage you from trying to do lotto, essentially. So it's where it comes from. So really, just look, it comes from gambling initially, but some good things have come out of it at least. And so this is the question that I started with. I don't know why this is the one. They're rolling a 2 dice 24 different times for some reason. And someone's prepared to pay you even money, which means if you bet $1 and you get if you get at least one double six in those 24 rolls, you get double your money back.
I'll do that.
Yeah, I'll do that as well.
So is that a fair odds to pay for it or not?
Well, odds are in your favour.
It's 1 in 36 and you get that 24 times.
Can I put the dice in the oven for a bit?
No.
It's a 1 in 36 chance and you get 24 of that.
So that's pretty bad.
That's pretty good.
24 times, how wide's the tree? It goes down.
No, it times.
Okay, so in order to answer the question appropriately, you need to have some mathematical framework to be able to talk about it, which you know, right? So as you're describing, it's a 1 in 36 chance of getting a double six on one roll, and therefore you could work it out over 24 if you want.
It's pretty good.
If you wanted. The answer is that it's the multiplied, so the expected amount of money you'd get from it. So the 2 is that's the amount of money you'd earn from winning. Is a $1.02. That's the expected return on for investing $1.
That's pretty good.
Which means if you play the game over and over again, eventually you'd make money from it.
Be a millionaire.
You'd have to have a lot of money at disposal just in case you lost a lot to begin with. So you wouldn't put all your money on it in the first chance because it's just slightly better than 50% chance of winning. Just slightly better than 50%, not much better. So it's like 51% chance, I think it is. So you need to, in order to work that out, when it's such a close call like that. So what they used to do before they did probability, they just play the game a few times and just count how many times they won. And if you win a lot of the times, you go, well, that's worth doing. In this case, it's pretty close. It's hard to tell that from just even doing it lots of times. You need the mathematical model for it. And although I don't encourage games of gambling, still having probability at disposal is a useful thing to do and a good way of making things more precise. So just some terminology. A common way of talking about probability is the probability of something happening. And well, how can I talk about that something? It's just useful to talk about sets as a way of all the different sort of things we want to happen. So sets are the common terminology for it. So just some different words. So we want to talk about just doing something that has a random outcome. So I've got to give it a name. Let's call it an experiment. Let's give it a name. And so it has lots of different possibilities. We'll call it a set of outcomes. Basically just an experiment. For example, in the last case, the experiment was rolling at 2 dice 24 times. That was our experiment. Then the sample space is a set. It's a set of all outcomes. In terms of what we've talked about before, it's really the universal set in all sense of purposes. So we might as well use U. In other contexts, people use the letter S for sample space. So that's just a group of all possible outcomes. So for what's the sample space of rolling 2 dice 24 times? Well, there's lots of different outcomes possible. So you can imagine there's 24 rolls. You can work out the sum of every single one of them, whatever it might be. It starts being lots of outcomes. So an event is some particular set of outcomes that you're interested in. In terms of sets, that's going to be a subset of the universal set, or the sample space. So the event we were interested in the previous case was getting at least one double six somewhere in those 24 rolls. That was the event. So normally we just say, what's the probability of some event happening? Or we naturally use the word. So what's the probability of getting at least one double six after 24 rolls? So that's normally not to phrase it, but just so we can talk about the various bits, E and X, etc. There's some language. So the probability of an event is basically assigning a number between 0 and 1, which indicates the proportion of the time it happens. So you know this. Well, I hope you do. So probability has many synonyms in English. So some of the synonyms are chance or likelihood or proportion. They're all effectively synonyms. Even percentage can be as well. So English is a very flexible language. So here's some examples. Can you tell me what the probabilities of each of these things are?
0, 50-50.
You have a count of
100%.
So the first one, the probability is equal to 0 or 0%. Is that the same?
Am I flipping the coin? Am I flipping the coin? Because if I flip the coin, it's going to be about 70%.
Okay, so what's the second one? So the probability that the sun will come up tomorrow.
Well, yeah, that's 100%.
It's 99.9999%.
Oh, yeah, you got to account.
That's the chance it won't come up.
Factor in cosmic.
Okay, so the answer is either 1, if you want to think of it that way, or 100%. That's the same. So 100% and 1 are the same thing, just different ways of running the same number. And you're happy with that because that's what the answer Phil just told me. The third one, so if someone reckons they're a bit of a bias, can introduce a bias to it, maybe the probability is 0.07 or 70%.
It's a 1.
Yeah.
If it's actually a fair coin, like the question suggests, what would the probability for a fair coin be?
50%.
So 50% or 0.5. So we can write, so probabilities technically are a decimal between 0 and 1, but we like talking about numbers between 0 and 1 as percentages, and that's fine. And so I will happily interchange between the two. So in terms of, if you ever have to code it up, you'd have to use decimals. But the easier way to talk to everyone else is to use percentages, just like you've been doing in class just right now. And so it depends what you're trying to do, but they're just interchangeable. So, and I will interchange them quite happily. If you don't like me doing that, let me know, I guess. Okay, so how can we assign probabilities? So there are sort of three distinct sort of ways that can be done. We'll mostly look at just the first one in particular, and then the second one a little bit. The first one is to use a mathematical model. There are different mathematical models for assigning probabilities. I'll do the simplest one first, because that's the one you know already. That's the one you just used for the head tossing coin. And that is, if you've got a set of outcomes, if they're all equally likely, which is not true if you've got an introduced bias in it, which I was talking about a second ago. So if they're all equally likely, then the probability of any event happening is the number of ways of getting that event divided by the number of ways of anything happening. So the number of the size of the sample space. And we use that when rolling two dice. There's one way of getting a double six. There's 36 different ways of rolling two dice. So 1 out of 36 for a double six. We use that for that particular case. And indeed, that's the one you're more familiar with. Now that only works if all the outcomes are equally likely, and that is not always true. So let's do some examples. What's the answer to this question?
Four over 9.
I didn't say that. Wait.
Okay, so the answer is 4 over 9. So the event we're interested in is blue. There's 4 ways that are happening, and the sample space is there either red or blue. There's 4 plus 5, 9 different ways in total of happening. So 4 and a 9. Now, what have we assumed when writing that down? We're assuming that each ball is equally likely to come out. Is that a fair assumption?
Yes.
No, the red ball's more likely.
Oh, sorry.
No, there's 9 balls. Each of those individual balls. Now, there's having more red of them, so
Reach
yeah.
in there, the blue ball's just like huge, the red ball's tiny. Oh man, a tiny red ball.
Well, that depends.
Yeah, if you put glue on the blue balls or something like that,
Are you trying
it's
to...
like the bottom.
Are you talking about throwing a ball from the bottom of the bag or from the top of the bag?
So, and the answer is yes. That's a reasonable assumption, really. So, if we say probably it's 4 9s, which everyone said, well, a few people said, whispered quickly, we are assuming they're all equally likely. But that is an okay thing to assume in this case. But it's good to realise there is an assumption we made, and you got to think, is that reasonable? Okay. Who's played Game of Settlers Catan?
Oh, yeah, I actually have. It's very rage-inducing. It makes me so mad. It's like they draw a card like 3 soldiers, GG.
Okay.
Do you not know the...
Yeah, I know what you're talking about.
Yeah, it's like, the worst. And then you get tiles and you don't have any resources. It's terrible.
So, it's about a game of collecting resources, and each round you do not collect resources if the robber comes up. In particular, there's many other mechanics I could mention, but that's one I guess I mentioned. The robber comes out if you get soldiers as one is what you're referring to, but ignore that for the moment. You get a robber moving around if you roll a 7. How often does that happen?
Very often.
2 dice.
So let's make you more, give you more understanding. It's 2 dice being rolled, both 6-sided dice, and you add up the 2 digits. If the digits add up to 7, the robber gets to move along and no one gets resources. So
1/6.
What? There's 6 outcomes. There's 6 outcomes of 7, but how many outcomes are there total?
There's 2 dice, there's 12 now.
Are there?
I think it's 1 and 7. 1 and 6 twice.
Yeah.
There's 1 and 7.
okay, we've done some counting. So,
6.
so the probability, if I can ever get the writing thing going down, is number of times we get a 7. So that's our basic formula. So it's going to be the number of times of getting a 7, number of possible outcomes. So we can do the bottom one. So we roll. So the first dice, how many options has it for the first dice?
6.
How many options for the second dice?
6.
Do we add them or multiply them?
Multiply.
Multiply. Do you want one and the other one? So we're rolling 2 dice. So that's the same counting principle we did yesterday, just for a simpler case, really. So how many ways of getting there are 7? It's probably just easier to list them all. If you think about the ways of getting 7.
3 and 4.
So 3, 4.
5 and 2. 6 and 1. Vice versa.
But the other way, but you can get the other reverse
7
order.
and 0. Should we remember that?
So all of those are equally likely. So the first dice can be 3, the second dice can be 4 is one option. The first dice to be 4, the second dice to be a 3 is a different situation. Because you have 2 different dice here, they can be in the different ones. So there are 6 different ways you can get the sum of 7. So we've got 6 ways out of the 36 ways in total. And if you chuck in your calculator, using a fraction button, for example, you're going to get it's 1/6. Or as a percentage, well, that is 16.7%. As a percentage.
Oh, yeah.
Rounded, it's rounded.
Hello.
Now, which is the easier way of communicating it? As the fraction or as a percentage?
The fraction.
Depends, really. And they're both useful. So sometimes people understand percentages better than
I
fractions.
like the decimal.
So, in an exam situation, I don't care. They'll both mark right. In your assignment 2, when you have to do some probabilities, I'm expecting it to be written as a decimal. The few probability questions you've got there. So to be 0.167 to 3 decimal places, for example. And they're the same. So all those last 3 are exactly the same equivalent.
Your calculator should do that for you.
Yeah, that's right. Exactly right. Like it's not. You can convert between all of them using a calculator quite happily. And I'm expecting you to use a calculator for it.
Oh,
In many senses.
warn you were going to make us do it mentally.
If you wish, you can.
No, I'm good. No,
You
I
don't
like my
get any
calculator.
extra points. You probably lose.
I would never know if you didn't do it all in your head. Okay, so there are more complicated mathematical models than an equally likely situation too. We'll do some of these later. I won't tell you any of them right now. So one example is using a Poisson model to talk about how many different times you get something happening. So an example would be you want to know how many times people are going to come to try to get access to your server and do things from it. If they come in a random pattern, we can have a model to predict how often that happens, etc. And therefore you can work out if your server's ever going to, the chance of it being overloaded, etc. That sort of questions you might want to ask. So it's not equally likely that you'll get 5 people and 1,000 people come to your server. They're not all equally likely outcomes. Some are more likely than others. And so you need to have some more complicated model, but we'll do that later. So I guess the first way of doing probabilities is coming up with a model, and these models always have some assumptions. So the assumption of this, the one we just did, was that all outcomes are equally likely. Is that assumption seen to match real life? The answer is, for playing game Settlers Catan, that seems okay. Unless someone's been cooking the dice as you were suggesting before. So there's other ways of doing it.
It's perfectly legal to do that.
I wouldn't be playing games with you.
Now, what if everyone's doing it? Then it's fair.
If you're betting money, it's not legal.
Say anything about betting money?
Nothing.
Look, if everyone's rigging the game. No one,
Everyone's the game, so you wouldn't want to play.
if everyone's rigging, no one's rigging.
Ooh.
So the other way of assigning probabilities is looking at what's happened historically, effectively. It's called the relative frequency approach. And that is, if you just repeat something over and over again, and just count how many times it happens. So you just estimate the probability to the number of times the relative frequency of it's happening. And so that's if you've got really no model at your disposal, but you can just do things over and over again. And so where would you ever use that? Well, we do that commonly as well. So if you pick a random person on campus, what's the probability they're male? How do you do that?
This room? Very likely.
In this room.
In this room, very likely, yes. On campus, it's about 40% chance. Thereabouts.
20.
Of males.
Yeah, so 40, in terms of the student population on Bathurst campus, it's about 40% male, 60% female.
There you go.
Good chance of girls are smarter.
Women are smarter.
No, it doesn't say that. So maybe they are. I'm not.
hesitation there.
No, I'm like.
High percentage of
Females could easily be smarter. I'm not disagreeing. Just because there's more females on campus doesn't mean that they're smarter or otherwise.
Look at Corey. If you got a union, that means smart.
I'm still here.
So that's one way, relative frequency. So just one way, and we do that so by just looking at historical data. So if you ever do financial stuff, they often say, look how good my fund is by showing that how good we've performed in the past. They often then will say as a caveat, this does not imply that this will continue in the future, and that's always true. So the last 10 years, I think the percentage of males on campus in Bathurst is around about 40%. It does change up and down a little every year, but it's similar. But it doesn't mean it'll be the same next year. Like the new first years or whatever it might be very different. Who knows?
It's just organised.
So the last one, which I'll mention, this is my only slide on it, and that is basically using the idea of probability as a sense of belief, or educated guessing, I guess you want to put it. So maybe sometimes you can't get a direct model for it, and maybe you can't really do experiments, and basically you want to have an educated belief. So an example is Hawkeye in cricket.
I thought it was stripped here.
So what? I presume you know cricket enough that to throw balls around. If you know nothing else.
You watch the grass grow?
So what Hawkeye does is it has about I think it's 6 cameras, and all the cameras are looking at where the ball is.
I like the bunker, please.
And at every instant, so there's only I can't remember frames, so it's a bunch. Someone say 50 frames per second. That's probably not even that.
The cameras.
They work out the position of the ball using the 6 different cameras. Then between the two frames, the ball moves a bit, and because the ball's spinning, it doesn't have to go in a straight directory. It can move in its path, which is the whole idea of cricket. And so there's a time there when you don't really know where the ball's going to go. You sort of can guess, but you don't know exactly what it is.
It's in baseball.
So you basically use the idea of probability to indicate where the sort of places it might be going in the next instant. That's really an educated guess. So, and you just use probability to describe all the different outcomes it can be. Then what happens? Then the camera looks at the next frame, which is pretty quick, and it looks at it's moved, and it knows a bit of physics to know where it should have gone by gravity, etc. And the next instant, that's where it reckons the ball should be. It uses the camera to see where it really is and makes a correction, and then has a belief where it might be next. And that's how Hawkeye works. So it's a tracking system. It's called a Kalman filter, is the fancy word for it. So those sort of idea of a Kalman filter is used in all the tracking exercises. You can make them a bit smoother. So the problem with the cameras is that they may not be accurate. That's the problem with the cameras. They may not accurately predict the position. But if you have, even though 6 of them, they're still not accurate. So if you can see several shots over a run, that prediction might be more accurate than what the cameras can produce. And so you want to have a mix of what you can see and what you've predicted. It's a fancy way of doing it. And in order to do that, you need to have a sense of the probability of all the outcomes. So if you've done a lot of tracking and you're really confident you know where it is, then you go, well, I don't really care about what the next camera shot is, I pretty know what it's going to be already. But if you don't know, if your prior belief is not very strong, so you go, well, there could be lots of outcomes, then you're going to have to trust the camera a lot more. So having a sense of a probability of how good your current prediction is allows you to correct either a strong way or a less way. So another example is in when they're flying a plane, trying to work out what the position of the plane is at the instant. So normally they use GPS to work out where your plane is. But the problem is you don't access GPS every second. It's just there's a bit of a time lag in there. So in between all the GPS measurements, they're going to just have to use the instruments on the plane to work out where the plane is. Now, if the GPS goes down completely, that's a big, quite long time lag. In practice, it's probably fairly short. But still, you get an instant of GPS, a long time, you still want to work out where the plane is before the next GPS comes in. And the same sort of thing happens. When your GPS comes in, you get pretty confident where everything's are, and as you go, and time goes on, you're getting less and less confident until the GPS figure comes in to just recorrect stuff. And so probability is a good way of describing how confident you are in your belief. So it's really a way of measuring belief, but it is a useful technique. And all this is called Bayesian stats. So that's the most I'll talk about it really. It's a common idea used in computer science when you're trying to detect patterns or do tracking, that sort of idea. And so in a game situation, I presume they'd use things like Cowan filters in when you're trying to do tracking of hands for Kinect, isn't it, in Xbox? I presume that's how they do that sort of stuff. It's a guess. But Hawkeye definitely does that. So some things are commercial, and so they don't tell you what the hell they do it. Other times they're a bit more open. So that's just basic ways of probability. So the rules you apply for probability are the same for all three approaches. We're going to look at mostly the mathematical model approach primarily. So there are three basic rules. The first two you probably know already in one way or another. The last one I'll have to explain a bit more. So I'll do it in turn. So they're the formulas, I guess, is what you need to know. And the next thing is we need to know what the formulas tell you. I'll let you write them down. So I use set notation. So what does the A dash mean again? Not. So it's just PA plus P of not A is 1. You can see I've actually written them as order down here. What's this cap? It's AND, so it's probably of A and B. Close. And I'll explain the rest of it in a second. So again, you need to write the formula in a way that you're more comfortable with. So if you write the word not rather than dash at the top, that's okay. You don't want to use it. Okay, so the first one is the idea of a complementary event. We did this with counting the other day too. So the probability of an event happening plus the probability of it not happening is equal to 1. Which is another way of saying something either happens or it doesn't happen.
Yeah, 50.
Yeah.
50-50.
No, not 50-50.
It either happens or it doesn't.
Doesn't mean they're equal. It could be 70-30. So here's a picture format. This is a Venn diagram again. So the probability of being in the box, that's probably in the universal space, is 1. So it's 100% chance of being in the box. So either you're in A, which is the white circle, or you're not A, which is the green area. So one of that. So it's total probability of 1. We would normally use it by rearranging it this way here. So the probability of an event happening is equal to 1 minus the probability of it not happening. That's how you normally use it. And so it's the idea of in trying to deal with it probably directly, it's sometimes easier to deal with its opposite. And we did an example yesterday on counting for the same idea. Okay, so this is the game of Settlers Catan again. So the robber moves if you get a sum of 7. If you don't get the robber moving, that means somebody at least you can get to pick up resources. I can put it that way.
You get like 3 wheat and add it to your 17 wheat you already have.
Or if you got 17 wheat, then you should have been spending it already. Is the answer? But
yeah, but you don't have enough to get a strategic card or to buy anything else. You just have 17 wheat because you use just tiles.
okay, you need to learn how to do trading, I think. But anyway, what's the probability of not getting a 7? Total of 7 if you roll 2 dice.
5 and 6,
I guess. 6 on 6 minus 1 6.
So the probability of not sum of 7, you go, well, that's a negative thing. It's going to be, you go, well, there's lots of different ways of not getting a sum of 7. It could be 2, 3, 4, etc. Heaps of options. That just sounds too hard to do it all directly. So I'll do the opposite. So I'll do the opposite of that. What's the opposite of not summing to 7?
Summing to 6.
It would be summing to...
Oh, summing.
Oh.
No, summing
I reckon you're right.
to 6. Whoops.
Sum to 7. I should write down exactly 7 when I shouldn't have.
My mistake.
And what's the probability of the dice summing to 7?
1 and 6.
1 and 6. It's actually the result at the top there. And therefore 5, 6. And again, you can write it as a decimal percentage if you want to, but 5, 6 would be fine too. And the reason why we do that is because that's a much easier way of doing the calculation, right? Trying to list all the possible ways of not getting a sum of 7. There's lots of them. So if you go through it, there's 30 different ways, effectively, arrangements where that's possible. So, that's the first rule, so a useful one. And next one is the sum rule sort of thing, so it's OR. So the probability of A or B is given by the sum of the probabilities minus the probability of the joint. Let's just scribble all over this slide. So the A or B, again, it's just think as a union in the picture. So it's both the red and blue together effectively. So the probability of happening is either you land in A or you land in B. So in some sense, it's just adding the two circles. The probability assigned to 2 circles. The downside with that, though, is that you've counted the bit in the middle, the purple bit in the middle, twice. So you've counted it twice, you only count once. So we're going to have to subtract off it once, just to make sure we count it just to count it the right number of times. So getting rid of the overcount. And you can write it as A and B or A cap B, use the intersection symbol. That's really thinking of sets if you want to. So, and that's where the formula comes from. So that's the most general sum rule, so to speak, which doesn't look very nice. There's special cases when it simplifies down. What you're more familiar with, perhaps. Okay, so let's consider the 100-sided dice, which look like golf balls anyway.
They do. A rolled one is pretty great.
So
An isosphere?
I can't remember the Greek for 100 off the top of my head. I'm sorry.
No.
I don't know.
D100, isn't it? That's what
Yeah,
I call it.
D100.
So 100-sided dice. What's the probability that you get a something divisible by 2 or 5?
It's different to Roman. Yeah. Do I look like I'm from Greece?
Yeah. From Greece?
No!
Why are you telling me?
Okay, look, I just took the Germans pound less.
I should draw a little bit bigger than that. Okay, so I'm just going to write down. So I've got two different sort of situations. So the first one is divisible by 2. The other one's divisible by 5. So they're my two different categories. I want it to be one or the other, right? So the numbers that are divisible by 2 would be 2, 4, 6, 8, 10, 12, etc. I'm not going to write them all out.
Oh, skip a few hundred.
Skip a few. The ones that are divisible by 5 would be 5, 10, 15, 20, 25, etc. So you can see that some numbers are both divisible by 2 and 5. I think you know that already. And so we've got to work out how many there are in each sort of situation. So how many of them are divisible by 2? So what's the probability of being divisible by 2? So it's 100-sided dice, so they're numbers from 1 up to 100.
Yeah, 50-50.
So well, half them would be divisible by 2. And so that would be 100 divided by 2. Half of them would be. That seems okay. What's the probability it's divisible by 5? 20 of them. So 100 over 5. Now, it works so nicely in this case because 100 is divisible by 2 and 5. So you have to work it, if you had to do the same thing for all numbers divisible by 3 and 7, it's just a little bit more, you just have to fiddle the last numbers a bit more carefully, but I made it easier, that's okay. What's the last one? So the probability of being divisible by 2 or 5 then, using that rule I just said on the previous slide, would be the probability that it's divisible by 2 plus the probability it's divisible by 5. And then we have to do something else. What's the other thing we have to do? So the problem is we've counted the 10 and the 20 and 30, etc. All of those twice. We only counted once. So we have to subtract off the probability it's divisible by 2 and 5. So we've got that's equal to, divisible by 2 was 102, divisible by 5 was 100 on 5, minus, what's probably it's divisible by 2 and 5?
2 times 100 over 5. I really don't want to do that.
1,007, 10.
Hmm?
I've got maths.
Yay.
Okay, so let's think about it. If it's divisible by 2 and it's divisible by 5, well, you can just see the numbers. They're 10, 20, 30, 40. I mean, you can count them if you wanted to. So they're just numbers divisible by 10, really. So how many numbers are divisible by 10? Well, using the same trick we did before, it'd be 100 over 10.
So it's 100 over 2 times 5. 100 over 2 times 5.
Yes. Yep. because they have no common factors why you can do it. So you start producing them with common factors and things like that, it makes it much harder. Let's keep it simple. So the answer then is 50 plus 20 minus 10, which gives the answer of 60. So 60 different numbers are divisible by 2 or 5 in the end. Now, can you think of an easier way of doing that question?
In my head.
So, I think in reality, you really, although you've got an OR, you're really going to have to split it up into the separate cases. So if I didn't have a 100-sided dice, if you're going to have a bigger dice, I can't imagine what it looks like. 1,000-sided dice, be practical probably.
It's like a sphere.
It wouldn't sit anywhere, would it?
What number did I get? I don't know.
I think it'll work.
No.
You just think you're ready.
It was 9. No, wait, no, that's a 6. Where's the 9?
It wouldn't work at all.
I don't see it.
You'd have to have your level out just to get the top to work out what the top surface is.
Make up my buzz.
So you could do the same procedure for the other ones, and you wouldn't want to have to try to count every single number in the different options. You just want to have some sort of overarching way. And if you wanted to have something that's divisible by 2 or 5 and 3 and 7, you have to do a more generalised version. This is called the pigeonhole principle, which I won't mention any more than that, but the textbook does if you're curious.
Yeah, 100-sided dice doesn't actually look too impossible, like to read off.
It's not
So long as it's about yay big.
You just put a gyroscope in there with a little light showing up through the numbers.
Oh yeah, that's a genius. Well done.
Paul, you're a genius. You're a genius, Paul.
Well done.
You just have a heavy ball.
Oh,
Yeah, that's what they have.
Number of times.
okay, yeah, sorry. So what should the probability be? Thank you. I've just done counting, I haven't done. So, what's the number of ways are there of in total? So we should have done all these things. Thank you for fixing me up. That should be all of these over 100, right? So there's 100 different numbers possible. So that's should be. That's a half, 1/5. So half of them are divisible by 2, half divisible by 5, and 1/10 divisible by 10. And so the answer, if you sum all those things up, is equal to 3/5, or as we said before, so effectively 60% chance. Thank you. Okay, so the last sort of probability, which you have, probably, I think you have done at school as well. The last two you normally have seen, like that. The last two you've sort of seen at school, you know, one or the other. The other one, is one's called a conditional probability. You probably have seen it too. You just may not have seen any notation for it or thought of it in this sort of language. It's called a conditional probability. So just that's a phrase there. So it's P A vertical line B. How I'd read it out is what's the probability of A given B. So just when reading that vertical line, just reads given. It's the easiest way of reading it loud. It means what's the probability of A on the condition of B. So the vertical line just sort of means there's a condition there, which is why it's called a conditional probability in general. But just reading it as given is more sensible. I'll give you the formula in a second, but let's just give an example first to show you that it's more intuitive than the formula might suggest. So this is the latest CSU summary stats that I could get, which is 2014. So there's a bit of lag on it. So you can see.
Circle. It all came full circle. Like to the male-female ratio.
Yes. This is what I was referring to earlier. So this is the number of males, female, at say Orange and Bathurst camp. So why I picked those two campuses because they're the campuses I work at, if nothing else. So say you picked a student at random.
Just tiny.
What's the probability that the student is male given they are on Bathurst campus? Which is a very funny way of asking it.
Better 20.
So the more natural way of asking that, which I've got the next slide, but and that is, what proportion of Bathurst campus are male? The more natural way of asking it. So I reckon. So historically, it's about 40%. Let's see what it was in 2014. So I think in 2008, when I did the last time I did lectures on this, it was about 37.7% male. That's what it really was. We'll see what it is 2014. So how would you work it out? So I want to know what's the probability that someone is male given they are on the Bathurst campus. I'm trying to work out. So what proportion of the Bathurst campus are male? So the more natural way of saying English is probably to give the condition first. So like I'm looking at just the Bathurst people, which proportion of them are male. So the way to do that without any formula at all is to go, look, I'm just curious just about the Bathurst group. That's all I care about. So it's all relative frequencies. So in that particular group of Bathurst people, how many of them are male? What's the count of them?
1,192.
So that's the number. And how many of them in total?
2,580.
Yeah. And that would be the probability. So just using a probability idea before, the number of ways of getting that particular event happening, so that is male and Bathurst, divided by the total number of ways that we all want to consider. If you take that in your calculator, what do you get? This is where fractions aren't so useful to try to compare it with other stuff.
Or you can do that in your head. Easy peasy.
0.4.
Okay.
40%. What?
So it's exactly 40%.
That's crazy.
So as I said, in 2008, it was 37.7%.
Bet the 41%.
I don't know what it was in the years between. It could have gone up and down all over the place. Who knows? So I mean, that's not too different. I mean, you'd expect some fluctuation because it's random, really. There's some random element into it. But you can see there's a trend. There's more females than males on campus. Now, you guys, this room does not reflect that.
No, we don't.
You're here. So that's the idea of conditional probability. So just the formula for it. So the formula, which is the one at the bottom of the slide here, really, the probability of A given B, in general, it's a probability of A and B divided by the probability of B. That's how you work it out in general. So how we did it in this particular instance, how we did it in just that table example, we looked at the number of ways of getting A and B and divided by the number of ways of getting B, which is really this first one. That's how we did it just a second ago, that formula. But if you rearrange it a bit, you can get it into probabilities. So that's the sort of idea. And I said you have actually seen them before, so but you just haven't used this lingo for it at school. So if you did probability trees, the probability on each limb of the tree is the conditional probability, essentially, from this case. Do you remember those sort of things? So it really just the bottom formula is all you need to copy down. But I mean, although the formula looks bewildering maybe at first, I don't know what you think of it really. I'm just trying to suggest it is natural, and given an example, you may not be able to answer it without realising there's a formula underneath it all. It's really just the same one as always. And there's a number of ways you get into the event divided by the total number of ways. It's just the total number of ways in this case is we're just looking at just when B is true, effectively. That's really the extra situation we're looking at. Okay. We'll try this one. So, a 52 deck of cards. I mean, I don't know how much we know about cards or not about cards. What's the probability that a card will be a heart given it's an ace?
1 in 52.
1 in 4.
1 in 13.
1 in 52.
So we've got a few different answers there.
Hang on, there's 52 counts.
Is it guaranteed to be an ace?
That's to be a heart.
So what's the probability that would get a heart given that it's an ace? That's what the question says.
1.
So we know we have an ace. How many aces are in the deck? There are 52 cards. 4 of them. So you got 4. So there's only 4 possible outcomes that we're going to really consider. How many of those aces are hearts?
1.
One of them. There's only 1 ace of hearts. So the probability 1 out of 4. Now I didn't actually use any formulas explicitly. Just I thought through it. If you wanted to use formulas, it would be the probability of getting an ace and a heart divided by the probability of getting an ace. That's the other way of thinking through the formula. What's the probability of pulling out the ace of hearts? So there's one card out of the 52.
Yes.
What's the probability of getting an ace? Well, there's 4 aces out of the 52.
So 1 in 13.
1 in 13, if you want it that way. I'll write it there. I prefer to write that way because you can see the on 52s cancel out and you still get the 1 1/4. 1 1/4 just like we did before. So that's using the formula approach. On the bottom, you can see it's just as easy. I think just as easy just not to worry about the formula, just to do it directly. It is good to realise the formula exists because it's sometimes helpful to have it up your sleeve. What's the probability of getting a heart in general?
1 in 13.
So you picked a random card. What's the probability of being a heart?
1 in 13.
So how many hearts are in a deck?
1 in 4.
So there's 13 hearts
Yeah.
out of the 52, or it's a quarter. So the fact that the card was an ace didn't actually change the probability of it being a heart or not. When that happens, it basically said that the numerical value of the card and the suit it is are independent of each other. Because the fact it's an ace doesn't have an impact upon whether it's being a heart or not. Probability hasn't changed. So they call them independent. Now, time's about to run out, so I'll say more about that in my next lecture. I'll talk about special cases of mutually exclusive and independent. But those, being an ace and being a heart are independent of each other because the probability is not impacted by it. But we'll see more, talk about more about that later. So I'll see you guys in tutorials.
See my lad.
You are currently the only participant in the conference.